Welcome you all to this course on defects in material. So far we have looked at point defects and then looked at the defect called dislocation. The dislocation is the one, okay, the moment of which gives, okay, or the which is responsible for plastic deformation in the material, correct. Suppose by some means you assume that in some materials dislocations are not able to move that easily, then is there any option for deformation to occur? Okay. That is what we have to look at it. Okay. Or is it that plastic deformation by moment of dislocation is that only option? That is the question. So, let us first look at how deformation propagates by dislocation, then we will come to the next topic, which is what is the other alternate mode by which deformation can propagate. Suppose we take a solid block like this, okay, in which we assume that dislocations are present at different regions. When these dislocations under the action of a stress which is being applied, okay, these dislocations come out of that sample surface, then there will be a small macroscopic strip will be generated when the dislocation has come out of it. This means that the shape of the sample has changed, okay, that is what it is. Here what is essentially important is that, which one should understand, is that you consider this region, what has essentially has happened, it remains the same. This region, has it undergone any deformation? No. Overall shape change is there, but this shape change is brought about by movement of dislocations in some specific planes. That means that the deformation is not homogeneous, but the deformation is heterogeneous. Okay. That is what it happens in that brings about the shape change, and generally these steps under normal experimental techniques which are available for observation of the dislocations, okay, or observation of the microstructure, we will not be able to see the steps, only the overall, as if the whole shape has changed. That is how we look at it. And the dislocations may be uniformly distributed at so many regions. So, it appears it is macroscopically it has homogeneous deformation, but microscopically the deformation is still inhomogeneous. Okay. Macroscopically it appears homogeneous. Microscopically, when you look at it, from this region nothing has happened, this region nothing has happened. So, it is inhomogeneous deformation. That is what it gives rise to, okay, appearance which is macroscopically, because at the resolution which we look at it, it looks like homogeneous. Now, what is the other option by which this material can deform? Suppose it is not able to move, dislocations are not able to move. The choice which it has is that when you apply a stress, okay, either the material can fracture to relieve the stress, or there is another mode in which it should deform. That is, we assume that case that where the whole region has deformed like this. It was this region, it has been homogeneously sheared to this shape. Okay. Essentially, what has happened is that, and another thing which you consider is that when it has homogeneously sheared, because the deformation appears to be now homogeneous, because here it is heterogeneous, here if we try to find out what that angle is, okay, this angle S will be equal to tan theta, this angle, that is what the shear we define. Okay. That means that every point the shear is proportional to the height at which we are considering it. So, it is a homogeneous deformation. Okay. In this deformation, suppose we assume this case that we have because so far we did not consider any crystal structure, correct? Now let us look at some crystal structure within this. In this case, if we look at it, when a homogeneous deformation takes place, now all these regions have undergone some deformation. Every unit cell also has undergone a deformation, whereas here if you consider it, by this movement the crystal structure is being preserved, correct? Once the dislocation has gone through, nothing has happened, whereas here there is shape change for particular angle of shear, the shape change occurs in such a way that crystal structure is being retained. Okay. If such a thing happens, okay, that sort of deformation we call it as twin. That is, by a moment of a homogeneous deformation, we have gone into another orientation so that it is able to absorb the external applied load, okay, the energy put into the sample, absorb the load and deform. This itself we can consider it in another simple way, because if we consider this structure, suppose let us consider a structure like this. Okay. This will be easy to visualize and understand. To this structure, we are applying a shear, simple shear. Okay. Then now you look at these two. Essentially, by application of a shear, homogeneous shear, the shape which was initially like this, it has been transformed to this shape. Now you look at the orientation, this crystal, it has oriented in a different way, but the crystal structure remains that same. That means that it has gone to another orientation. Okay. This sort of deformation is called, which takes place in material by homogeneous shear, is called as twin. Okay. So we have looked at external shape, now we are considered the unit cell also, right? So only the orientation has changed. Okay. This sort of deformation becomes very important. Okay. So what essentially has to happen is that
more energy.
Exactly. That means that when slip is very difficult in a material, twinning will occur. That is the condition. Okay. So if slip requires less energy, if it can occur, then twin formation does not occur, deformation by twin does not occur. When slip is inhibited, then deformation by twinning occurs. The cases which it can happen is that, suppose we deform a sample, lot of forest dislocations are there, then the glide dislocations find it extremely difficult to move, but the external stress which we are applying, that stress is being increased, continuous pressure it is putting onto the sample. Then some of these regions can deform by twinning. So in many materials where slip takes place, at the end of the deformation, when the strain is very high, where dislocations find it very difficult to move, at those circumstances, twinning can occur. Is it clear? Okay. That is one. Then one more factor which comes. If a material, we take a polycrystalline material, okay, if it has to deform uniformly without fracture occurring in that material, then 5 independent slip systems are required for deformation to take place. This is called as the von Mises criterion. Okay. Many materials like FCC, FEC, BC, we have 5 independent slip systems are there. Like HCP metals like zirconium or titanium, there are only 4 independent slip systems are there. That means that by moment of dislocations only 4 slip systems are there. But if the material deformation has to maintain the material continuity, one more system mode of deformation is required. In such cases, the twinning becomes another mode, another independent mode of deformation. So in those material also we observe like zirconium and titanium, twinning could be observed frequently when we try to deform the sample. Suppose you assume that the twinning is not there, the material will be like a brittle material. It would have fractured very easily. Okay. Having said so far about twinning in a very simple way, now let us look at a little bit in detail about the crystallography of twinning. What can you understand of the science of these twins? Okay. Okay. How do we define a twin from a crystallographic way? If we have one crystal is there, okay, by a symmetry operation, that is any of the symmetry operation, if another variant is being generated of that crystal, these two will be, the relation between them is essentially called as a twinning relation. Okay. That is what I have written here. When a crystal is made up of parts that are oriented with respect to one another, according to some symmetry rule, the crystal is said to be twinned. These regions are connected. So that means that twinning need not be by a mechanical means. It could occur otherwise also when crystallization takes place, when from solid to liquid, when the transformation takes place. Even in solid state transformation, we can have regions which are related by twins. Okay. Okay. So what are the symmetry operations which we know? They are reflection, rotation and inversion. All these symmetry operations, if crystals or two crystals are related by these operations, we can say that they are twin related. Okay. That is common rule for twinning is, this is what essentially it is. All the three are possible and all these type of operations have been observed. Okay. Let us try to understand how the crystals will look like when this sort of deformation takes place. Okay. What is the simplest example which we can take of a reflection twin? Mirror image which we can take it. One is our body itself. Across this one, if we take it around this axis externally, we are related by a mirror symmetry. So this half and this half are twin image of the twin related. Okay. Other way in which we can, you assume the case, this is just a hypothetical case. Suppose across this it is not related by reflection, it is by rotation, then what will happen? How will it look like? One eye will be here, another will be at the back, correct? So that sort of operation also is one, that is also related by twin. Okay. Okay. Then the contact between this area where the twinned and the untwinned region meet. Okay. Suppose you assume that this itself is, assume it to be a crystal which is there like this. Okay. When load has been applied, okay, this part remains like this. This part has deformed and reached the mirror image. So this plane where they join together, this is called as the composition plane. Okay. That is where the twinned and the untwinned region meets, or this is also called as the twinning plane. Okay. So essentially across this plane, everywhere a homogeneous shear has been applied. That is how this deformation has occurred, correct? I mentioned that twinning need not occur due to deformation also, but due to nucleation also. Especially in non-cubic systems, this sort of process occur. Okay. This is one example which I had given. Here if you look at it, the unit cell now here is like a, this is one unit cell, this is another unit cell. Okay. This is nothing but a tetragonal, body center tetragonal unit cell. It is a projection which is being shown. If we look across this plane, okay, across this plane, both of them are twin related. Okay. This sort of process can occur during nucleation. Example, we can take it. Suppose a material at a high temperature is FCC. Okay. From FCC, it undergoes a transformation at low temperature to tetragonal structure. Okay. And let us assume that when this transition, this transformation is occurring, okay, the A lattice parameter remains the same, A and B, the C lattice parameter has increased. Then if we just look at a two-dimensional analog, okay, initially which is essentially an FCC structure, okay, it has now become slightly, okay, this is the C direction. Okay. The crystal can form when it is nucleating in a single crystal. In some region it can form with the C axis along the C axis of the FCC. In one, or the cubic system, in one it can form with its C axis along the A axis. In another it can form with its C axis along the B axis. That means that three possibilities are there. All the three can occur. All the three possibilities will occur simultaneously at different region, but one of them will occur at a particular time at a particular region. Suppose such a transformation has occurred. When they come and join together, when the transformation takes place during time, then if we look at this structure, okay, and the structure which is forming in another region, with this, when they join together across one interface like this here, these two are related by a mirror, correct? That is precisely what is being shown here, is that here C axis is in this direction, in this one the C axis is in this direction, then across the interface now you see that they are related by twin, as if this whole unit cell we had given a shear and deformed it homogeneously to bring it from this structure to this particular structure. Okay. This aspect of it we will now consider. Okay. So, essentially what we have seen it is that there are many ways in which shear could be, there is many ways in which twinning could occur in the material, not only by deformation, but during phase transformation also twinning could occur. When the twins which occur due to phase transformation, we call them as transformation twins or orientation twins. These are all the two, because one orientation variant is there, another one which is oriented in a different way, okay, but the crystal structure remains the same. They could be related by a reflection, or they could be related by a rotation, or they could be related by inversion. Okay. Let us just concentrate on this FCC lattice itself. Suppose here with the C axis has formed here, if another one forms with a C axis along this direction, this cubic unit cell, but since the symmetry is being maintained, A, B, C we can't distinguish them, correct? Because of which, whether C axis is in this direction or C axis is in this direction, as far as the structure remains cubic, it remains identical. We cannot distinguish them. That is what it happens in the case of a normal transformation when FCC itself is there, when different nuclei form. Whereas when a transformation occurs where we are able to distinguish the C axis, then we can immediately notice that these nuclei, we can distinguish them by looking at it, telling that on which direction the C axis forms, we can identify them. And then we can find out what is the symmetry relationship by which these two are related. If they are related by the symmetry relation, then we call them as twins. That is how we have defined the twins now, right? Here I am just showing, taking an FCC lattice, how twinning is occurring. Okay. The stacking sequence in FCC, okay, is ABC, ABC, ABC in a perfect stacking sequence, correct? In this lattice, if I apply a homogeneous shear, that is the plane which is here, A, B, C, these are all what has been shown here is a 1 bar 0 projection. On that plane it is being projected. These ones, if you look at it, this is 1 plane. Okay, this is another 1 plane. This is 1 plane. Only the projection is being shown in that 1 bar 0. This is A, this is B, this is C. If by A by 6 112, okay, if I move the next plane which is an A plane which has to come, okay, it occupies a position which is corresponding to B. The another one corresponds to a position A. Okay. So, this is what we can do, that if I introduce a stacking fault here, now it will become ABC, ABC, this will become B, this will become C, A, B, C, like that it will go. Now, if I introduce a fault in the next plane, that is, then what will happen? The stacking sequence changes to ABC, ABC, B, C becomes A, B, C, A, like this it goes. Now, across this if you see here ABC, here CBA, correct? The stacking sequence is reversed. Okay. The same thing when we look at the projection of the crystal in 1 bar 0 direction, now we can say that these are related by a reflection, mirror symmetry is there. So, these two regions we can call them as twins, or that is, this small region is essentially a twin which has formed within them. That is, when the stacking sequence reverses, then we can say that the twin is formed, but this is a visualization of the same stacking sequence of the crystal. That is what we have shown here. Is it clear? Okay. This we had shown that by movement of a partial it can occur. Now, the next question comes is that means that partial means that the material should have a low striking fault energy, correct? Only if a low striking fault energy is there, then only this sort of a shear can occur and twins can form. That is one criterion. The materials which have low striking fault energy, what has been seen is that, especially suppose we take gold, evaporate it and allow it to condense on a cold substrate. When it condenses, it has been seen that lot of twinning occurs. These are called as micro twins. That is, it's a growth only is taking place. This is because since the fault energy is small, okay, twins, that when by stacking one layer on top, growth takes place. Sometimes stacking sequence, instead of B atom coming a position, C atom can come to a position, and like that it can happen, it can reverse again. That means small regions you find that in the growth are twin related. This happens from vapor to solid, liquid to solid, as well as in solid to solid transformation also. This sort of, that solid to solid transformation which we can think of is, take copper, gold, we cold roll it, we anneal it at a very high temperature. If you look at the annealed sample, what do we observe? In the grains which are connected like this, within them we find lots of regions like this which are related. These are all twins. These we call it as annealing twins. Okay. That is from the completely deformed region when defect free, dislocation free regions are growing. The atoms are arranging itself in such a way that sometimes the stacking sequence is changed. Those regions we call it as annealing twins. Okay. Then twins can occur during or glide twins, the deformation twins we call them. Then another is that when martensitic transformation takes place, okay, there also to accommodate that strain, twinning occurs within the material. In addition to it, in most of the materials where the slip is difficult, they are hard materials. If you look at the microstructure of those materials, okay, when they have solidified or minerals, if you take it and look at it, we find that many of the minerals, plenty of twins will be there. Okay. These are formed during solidification or under extreme pressures under which they are subjected to beneath in the earth, okay, under which this sort of transformation might have occurred. Okay. So, what we have done is we have briefly looked at what are the ways in which twinning can occur. Okay. In aluminum, if you look at it, twins does not form at all. The reason is that the stacking fault energy is very high. So, whenever one layer after another, even during growth when it happens, okay, fault do not form. This I believe could be due to the reason that if we look at one layer, a hexagonal packing layer is which is ABC, means that they are stacked on top. If I take an A layer, there is a B site and a C site is there to which the atoms can go and occupy. Okay. This is just pure probability by which they can occupy. But if when that occupies, it forms a crystal structure also. The layer beneath them also will have an influence on what sort of a structure, because if any stacking fault is formed in FCC, that is nothing but a unit cell of HCP. That means that the HCP structure should also be, the energy which is required to form them should be very small. Then only this sort of a transformation can occur. Suppose the energy is high, that structure which it forms has got a high energy, okay, then it would prefer, because this is a thermodynamic condition which we are applying here, that it would prefer to remain in the FCC state. That is what it happens in the case of aluminum. Okay. When fault energy is high, okay, stacking faults do not form. Okay. So, deformation twin is not seen, nor even a growth twin is seen. That means that the type of annealing twins which are seen in the annealed microstructure of either copper or gold, those things we do not see it in aluminum. Okay. Whatever be the way in which these twins are formed, what is the mechanism by which twins are formed, there is something which is a common crystallography which is involved in that. Okay. That remains that same. What we would try to look at it is first look at this crystallography of twinning. Okay. Let us just look at a simple shear. Okay. In a simple shear, what we do is only that if you look at the strain tensor which is being given, it is only one direction we are giving a simple shear. Okay. What is being shown here is that we assume that the original shape of that sample, we assume it to be a hemisphere. Okay. This hemisphere, when we apply this shear, what we are applying, it is called as a simple shear, but it is a homogeneous shear. That means that every region will be deformed proportional to the height by that multiplied by the height multiplied by that tan alpha, that's the way the displacement will take place. When such a thing occurs, the way this will become, because at this region they are joined together because the strain has to be 0 as the height increases. So essentially what we can see is that this is how it happens, correct? Then here, like this, each point, this is what we had shown here. Okay. Another interesting observation in this is that there is at one particular point, that is from the center, if I look at vectors which are joining to the surface, okay, I can look at these sort of vectors, correct? After shear, this vector has changed to another vector. You take from here, when it has deformed to here, this vector has now become this one. That is, the vector length is not the same. So there is a distortion of the vector is taking place. Okay. But at this point, the deformed one, from it has, after some deformation from here to here, when it has come, the vector length remains the same. That means that in this sort of a pure shear, one of the property is that there is one direction which is distorted, but it is rotated. Okay. Yeah. So it is just rotated like this. But all other planes, there's under. So this is only a direction which we are considering it with respect to. Suppose we consider to be part of a surface which is essentially a cut, essentially a cylinder. Okay. Since shear is being applied, there is a plane which is passing through this. This plane, if we consider, that plane also remains rotated but undistorted. But here there is one plane is there which remains neither rotated nor undistorted. Okay. So there are two types of planes are there. From the after the deformation, there is one particular plane which remains joined together, that is called as the composition plane or the twin plane, over which the materials are the deformed and the undeformed region is meeting, because you assume that this is the other part of it. So this part with respect to it, when a deformation takes place, it has changed. So this is the plane over which they are joined together, but there is a plane as well as a vector, we can see that both of them are getting rotated. Okay. That means that there are two planes that are there, which even after deformation the plane remains that same as that of the original plane. This is a property of homogeneous shear. Okay. When whatever be the amount of shear which we are applying, suppose the shear becomes very small, this would have become like this, it would have happened. Then the vectors which are there, maybe this vector and this vector are different plane. That means that this is an inherently a property of this homogeneous deformation. But for some deformation, some strain, when that is the shear from here to here. So here to here is what the displacement, and this height, if we take the ratio of it, that will automatically give what is the simple shear which we are applying. The magnitude of the shear we can calculate it. Not only that, for a particular value of the magnitude of the shear, when this change takes place, it goes from one orientation to another orientation which is identical to it. When such a thing occurs, then we say that twins have formed or they are twin related. That because they are related by some symmetry operation. That how we can consider it is by a, that I will come to it now. Okay? Is it clear? Okay. I have just looked at a crystal structure. This is an FCC lattice. Okay. the same as what I had shown here. This is the plane which I consider as a K1 plane. Okay. These are 1 on 1 plane, all are 1 on 1 planes. I could have chosen any one of the 1 on 1 planes. Okay. And similar to this, this is the other 1 on 1 plane in the lattice. You forget the red atoms. Okay. You consider that this is the lattice which is there. Across this 1 on 1 plane, above this plane, in all other 1 on 1 plane, in this direction, which is 1 on 2 direction, okay, 1 on 2 bar direction, the specific one, I am shifting it every atom by a by 6 1 1 2, okay, a by 6 1 1 2 bar. That means that this atom is shifted by that vector, it comes here. Okay, that is what I had. When I give a shift to this atom, all the layers above will also shift by that same way. Then in the next layer again I give another eta. It is equivalent to deforming the second layer by 2 eta, right. Eta is the shear vector which is being given on every layer. When I do that, this atom will move from here to this position, this atom will move from here to this position, this atom moves from here to this position, okay, this will move from here to this position. Like that, each of them are moving to different position. Then when I give it in the third layer, okay, this is 3 times eta, it moves from here to a position which is identical to the original one. That means that when we looked at the stacking sequence A, B, C, this has become from the A layer has gone to B layer, then B layer has gone to C layer, okay, then here the C layer has gone to an A layer. Okay, so the stacking sequence have changed. If you look at this one, this is during shear what happens. So every layer has undergone a shear eta, 2 eta, 3 eta, that is with respect to height the shear is taking place. That means that this is a homogeneous shear which is occurring in the material. Okay. And what I had shown here is just the projection of it. Now if you look at it, after the transformation, this sort of a cell here has transformed to this sort of a cell. Now you look at these two cells, they are related by reflection, correct, across this plane. That means that these two structures are twin related. This same thing I have just shown it in a different way, where I have removed all these atoms, because here I had shown both the positions before shear as well as after shear. This makes it little bit difficult to imagine. Here I had shown only the lattice structure is being shown, not the atoms. And now when the transformation has taken place, now we can see that these two are twin related, correct. And essentially we can see that this vector, okay, from here to here has been transformed from here to another identical position, right. This is the vector which is rotated but not distorted, correct. And here this is the plane which is the K1 plane, okay. This is called as the composition plane, and the shear is being always given simple shear in this direction, homogeneous shear which we are giving it. So it generates in the deformed that is this plane K2 plane which is called is the plane which has also rotated but undistorted, okay. So these 4 terms, okay, are very important in understanding twinning crystallography. That means that there are 2 planes are there, okay, which are undistorted, okay. By deformation they do not undergo any transformation, but only they undergo a different orientation change. Similarly to directions are also there, okay. And if we look at what is the shear vector which corresponds to this for this FCC lattice, is we can calculate this, it will turn out to be 0.707. So this is a very high shear. Only for this shear twin related structure will be formed for these planes. For some other plane, if you consider, it may be a different shear vector which will be required, okay. So, that is exactly what I had shown here. Okay. But what is the lattice which we have considered here? This lattice is a Bravais lattice. We should understand that it is a Bravais lattice which we are considering it, and twinning is considered always in terms of shear of the Bravais lattice. Okay. And this mode of deformation also can occur in a material. Okay. So, whenever material has to deform, it has got two modes in which it can deform. One is by shear or by twin. There is a third mode of deformation which is there, is like a viscous flow, very high strain rate deformation, okay, like when you fire a bullet or an explosion takes place. What is the mode which the material will deform? Then we call it as some shear band propagation. That is, as far as the material has become highly viscous like a fluid and it deforms. That is the third way. That is at an extreme rate of deformation. Otherwise, under normal conditions of deformation, when we do that, these are all the two modes by which the materials deform. Is this clear? Okay. And another also is that by this homogeneous deformation which we have introduced it here, we have generated, this is one orientation, another orientation which we have generated of the crystal, correct? And these two are related by a symmetry operation. Okay. Here we considered as across this plane, it is mirror reflection. But if you look here with respect to this direction, if I take it, that is perpendicular to this, if I take a direction and give a rotation of the old structure, I could get the new structure. It is related by rotation also, 180-degree rotation. And in this direction, like for example, here around this direction eta 1, if I give an 180-degree rotation, what will happen? This from bottom one, the top one will be formed. Okay. So, these are related by both reflection and rotation, and the terminology which is used is, this is called as a compound twin. Okay. This we will come back to it. Just wanted to show that here many types of twin process occur together, that many types of symmetry operation by which they are related, but all need not exist. Maybe by only one symmetry operation related also it is a twin. Okay. That is what is seen in most of the non-cubic systems. That we will take up later some examples and look at it. Okay. Before we do that, if you look at a material, how does it look like when I deform it? Okay. If a material deforms by twin, or assume that a material is deforming by slip. Okay. Suppose this is the shape of the sample. Lot of dislocations have passed through the sample. Okay. Various different forms, and they are passed through it. Then the material would look like this way. Externally we can see this, correct? This is how with a step it happens, correct? How this can be verified whether it is occurring or not is that, suppose on the sample I draw a line. In a polished sample I draw a line before I am deforming the sample. Then it has deformed by slip which is taking place in this line. Then what it will happen? This line will be like this. This line will be shifted by this. These lines with a gap it will occur. That means that deformation is discontinuous. If the deformation is continuous, they should have tilted, they should be joined together. That does not occur. Okay. This is one way. Let us take the case when the material deforms by twin. Okay. Like this is the region where the twinning is taking place. Assume that within this band. Okay. When twinning is occurring, then what will happen is that the rest of the regions remains in that same position. This is what it happens. There is a overall a shift which has taken place. So, from this direction how much is the shift? It is getting tilted we can find out what is the macroscopic strain which is involved, correct? And in this, suppose I have drawn a line, what would have happened? After twinning, when this happens, this line also would have, but continuity is being maintained. This is one way in which we can immediately find out whether it is twinning or slip. But the same thing can happen for morphostatic transformation also, which I will be talking about when I talk about morphostatic transformation, maybe after a few lectures. Okay.